So in this set of Snap Circuits videos, we're looking at project 641 to project 655. Oops. So with project 641, we have the AND gate. There it is in the book, and here it is on board. So before I get started, again, this is talking about logic gates and logic operations. And almost a decade ago, I actually did a video using the Snap Circuit system to visually show how logic gates and logic operators work. I'll probably have a little card or description somewhere on the video here linking back to that original video, which is one I plan to kind of redo in the future because there's been some more stuff since then that I would like to cover and kind of look at again with that. But anyway, with the AND gate here, we have a 6-volt supply, and we have our 7-segment LED, which is acting as our output, which you see right now is displaying a L on there. And for the actual logic operation and what's being controlled here, we have two conditions here. We have our toggle switch and our press switch. Those are going to act as our variables for the logic here. So we'll assume that the slide switch is one of them and the press switch is the other one. And depending on whether those are turned on or true, as we call it, then we'll determine whether the output condition is true or false, or in the case of this, low or high, because it's displaying an L. And our PNP and NPN transistors are kind of handling the logic portion of that depending on the conditions here. So when we have our switches in the off position, we have two false statements here. So we have a false statement on our 7-segment LED, and so again it's saying that it's low. And if you ever get into diagnostics, especially when you're looking at cars and stuff like that on the systems that they have on them, they're usually trying to figure out if a circuit is low or a circuit is high, and that's basically a form of logic control with cars for controlling certain things on them. And so we're kind of looking at it like that here with the L and H, saying a low or high condition, again, true or false. So again, both of these are false, so we have a false output on our 7-segment LED. If I turn on the slide switch, well, the output condition does not change. Although this is true, this is false, and it's still false here because this is an AND logic gate. So the catch is both conditions need to be true before we have a true output on our 7-segment LED here. So we have a true condition for our slide switch, a true condition for our press switch because both of them are turned on, and by that we get a true or high condition on our 7-segment LED. So that's how the AND gate works, project 641. So project 642 is the NAND gate. So it's basically going to be opposite of what we have, and we can do that very simply by just rearranging the wires here. So now with a NAND gate, it's an AND gate with a negation on it. So an N usually means a NOT operator or an inverter. So whatever output the AND gate normally has, it's now going to be opposite. So that's how we get the NAND. So right now, circuit is the same, but we have both our slide switch and our press switch are turned off. So they're both a false condition. But according to our 7-segment LED, we have high or a true condition on the output there. So again, like a regular AND, if we only have one of these conditions true or turned on, the output condition is not going to change. It's only when we have both the slide switch and our press switch both true or turned on does the output condition change. And in this case we get a false condition or low on the output because again this is a NAND gate, so it is opposite of what the AND normally is because we're negating the normal output. So when you have either one of these false or both of them are false, you'll always have a true condition. It's only when these are true do you then get a false condition on the output with the NAND gate. So that is how project 642 works. Now we're going to look at project 643, which is the OR gate. So let's rebuild the circuit a little bit here. Change these back around. And just change these. So I need a number 3. Where is it? Or can I make do with a number 2? Hold on. So now we're back with project 643, the OR gate. There it is in the book, here's on the board. So with the circuit slightly reconfigured, we're now looking at the OR gate, or OR logic operator. So as opposed to the AND, where we had to require both conditions of our press switch and slide switch there to be true, or in the ON condition to have a true output, with an OR, you see, with both of them false right now, we still have a low output or false condition on our 7-segment LED being represented. But when we turn just one of these on, like the slide switch, we now get a true condition or high output on our 7-segment LED because it's OR. So we can have the slide switch here to be true, we can have the press switch to be true, or we can have both the press switch and the slide switch to be true, and we'll all have a true output. It's only when both of them are false do we actually have a false output on the 7-segment LED, and that's why it's called an OR. You can have the first condition or the other condition true, or both conditions true. So that's how that operator works. So with project 644, get the next page here. So now with 644 we have the NOR gate. So it's again similar to how the NAND worked before. I'm just going to reorient the jumper wires here. So with a NOR gate, it's pretty much just like how the NAND works in relation to the AND gate. So with the OR, if one or both of these conditions with these switches here were true, then we'd have a true output. But now you see when both of them are in the false condition, we have a high or true condition on our 7-segment LED here, because NOR, just like the NAND, it's an opposite of the original operator. So we have the OR, but now we're negating the output, so it's always going to be opposite of what the normal OR logic gate or operator works on. So now if we were to turn one of these switches on, like the slide switch for instance, so now we get a low or false condition on our output. Same thing applies with the press switch, or when we have both of them on, because again it's a NOR, so we're negating the normal output that we would see. So that's how the NOR gate operator works. Now we're going to look at project 645, which is the exclusive OR gate. Here we have project 645, the exclusive OR gate. There it is in the book, and here it is on the board. Now, the exclusive OR is different from the OR or the negated OR, the NOR, because in this case, with an exclusive OR, and I kind of worded this in my video on logic gates to make it kind of sensible, it means either or, but not both. So in the case of this, as you see right now, with both the press switch and the slide switch turned off or in a false condition, we have a false output on our 7-segment LED because there's no output on it. When we turn our slide switch on, we get the H there indicating a high or true condition when we have our slide switch turned on. So our slide switch is true and our press switch is false. Now if I go up to the press switch after turning that off, so now the press switch is true and our slide switch is false, and we still have a true condition on our output there. So far it's behaving like a traditional OR. However, with an exclusive OR, when we have both our slide switch and our press switch turned on or both true, we now go back to a false condition on our output. And this is the exclusive part of the exclusive OR. Again, as I say, you can have either or, but not both. So in the case of an exclusive OR, either the conditions can both be false or they can both be true and you'll have a false condition. It's only when you have a single true condition on just one of them, whether it's the sign switch or the press switch here, that you'll have a true condition on the output. So that's how Project 645 works with the exclusive OR. Now I will say they don't have ones in the book here that I see for the NOT operator or for the exclusive NOR, but again I covered that in the video I did long ago, which again, as I say, I'm planning to revisit, so you'll be able to look at those later on. So anyway, we're moving on to Project 646, which is the high pitch oscillator. So here we are with Project 646 through 649, and the high pitch oscillator. There it is in the book, and here it is on the board. So we have our 6-volt supply, and it's going to our speaker, which runs through our red LED down through the NPN transistor here. And that's being controlled by an output from our transformer, which is stepping down, as you see from the configuration here. And on the other side, we have the actual oscillator circuit that we're going to be hearing and seeing. So we have our 100 microfarad capacitor being fed, and then it runs through our 2.5, 3-volt lamp here, pretty much acting as a 3-snap. And then it goes through one of our resistors into the base of our PNP transistor, which then turns the PNP transistor on and off. We have our variable resistor, again controlling resistance to another resistor that is across our whistle chip and also the base of the PNP transistor here. And then these ground connections are all going into our transformer. So as the circuit oscillates, it creates an AC signal, which then of course will turn our NPN transistor on and off, and we'll hear the oscillation both through our speaker and visually see it through our red LED there. So we set our variable resistor all the way to the top, and when we turn the circuit on there, you can see our LED is pulsing, and you can hear it also coming out the speaker there. And if we adjust the resistance, we of course change the frequency of the oscillation, making it oscillate faster and faster. So that's how Project 646 works. Now Project 647, we're going to change out the whistle chip here, because this will change the rate of oscillation in the circuit, or the frequency, because the whistle chip itself acts as a capacitor in this case. So we're going to put the C2 0.1 microfarad capacitor there. And since we're increasing capacitance, like we have seen in previous projects involving oscillation circuits, when you increase the capacitance, you tend to decrease the frequency of the oscillator circuit. So now with that capacitor in place of the whistle chip, it's now oscillating slower, and you hear that the sound has changed because it's at a different frequency now. But again, as usual, if we change the resistance on our variable resistor, we can speed up the oscillation. So that's how Project 647 works. And now Project 648, we're going to increase the capacitance even more. So now we're going to go up to our 10 microfarad capacitor, and these are polarized, so the plus is going to be facing toward the top because that's where our current is coming from. So as you'd expect, when we increase the capacitance on this, the circuit's going to oscillate even slower. Again, with a lower frequency as well, so you can hear the tone is not as defined as when it was oscillating faster with the smaller capacitors. So that's the max setting on the variable resistor. As you can tell, it's not constant as it was with the previous capacitors because there's just so much capacitance here now. So that's project 648. So the last one, project 649, takes us all the way up to our 470 microfarad capacitor. So we're going up quite a bit, about 47 times more capacitance. So when we turn the circuit this time, the oscillation of the circuit is pretty slow. So again, pretty low frequency. So that's it for project 649. Now, one additional little thing you can try in here that's not mentioned in the book is not only do you have the capacitors to control the frequency and the rate of the circuit oscillates, but you yourself can act as a capacitor. And because of that, So that was project 649. Now, one of the interesting things that you can do with the circuit here that's not mentioned in the book is that you yourself can act as a capacitor because your body has a little bit of capacitance in it. So we can actually use ourselves as a makeshift capacitor in the circuit to control the rate of oscillation and thus the frequency of the circuit. So of course without any capacitor there, the circuit will not oscillate. But if I were to take my two fingers here, see, now the circuit is oscillating. We have the variable resistor at the lowest setting it can go, but the circuit is actually oscillating pretty fast. It's a pretty high frequency if you're able to hear it there. And so again, that indicates that our body, while it has capacitance, it doesn't have a whole lot in comparison to the actual capacitors we have here in the system. But it's a little fun thing you can show with your circuit there. So again, that's it for project 649. So now we're going to move on to project 650, which is the segment jumper. So here we are with project 650, the segment jumper. There it is in the book, and here it is on board. So with this, we have our 7-segment LED again, and it's got a couple of different segments connected up here. Our alarm IC is being fed. We also, of course, have 6 volts powering everything. We have our red LED coming down to the collector of our NPN transistor, and that's connected again to our top portion of our segment LED. And then we have this set of resistors, both our R4 and R2 resistor, coming down and then connecting to the bottom segment of our 7-segment LED. And then the base of our NPN transistor is receiving output from the alarm IC, which will control that, and it's got a little 10 microfarad capacitor across it. And then we have our green LED, which is pretty much limiting everything, but it also allows us to see the changing current levels as this circuit turns on and off. So when we power it up, you see a couple things happening. Number one, our 7-segment LED is going back and forth between the bottom 3 segments and the top 3 segments, and you notice the bottom segment is dim and the top segment is nice and bright. As when the top segment lights, it also lights up our red LED, and if you pay attention to our green LED down here, it alternates between being dim with the bottom and bright with the top segments. And what's happening here is that normally current is going through our 2 resistors here and lighting up our bottom segments there, and because there's resistance, they don't glow brightly. But when the alarm IC provides output to the base of our NPN transistor here, that turns our NPN transistor on, and instead what happens is all the current bypasses our resistors here and goes to the base of the NPN transistor here, and then of course it turns on the red LED in the top segments because that's what's connected across it, and then we see that increase in current reflected across our green LED there. So that's how it ends up alternating between the top and bottom segments. It normally uses these resistors, but then once the alarm IC and NPN transistor get powered on, no more current goes through these resistors, it ends up going through the top portion of the 7-segment display. So that is how Project 650 works. So now we're going to move on to Project 651, which is the decimal point and zero flasher. So here we are, Project 651, the decimal point and zero flasher. There it is in the book, and here it is on the board. So we have our 6 volts with our slide switch turning off everything on the circuit. We have our 7-segment LED with the various segments that we'll see. Basically, we got the 0 and the decimal point being powered. We're using our alarm IC, which is being outputted to both our speaker, and then it also runs down through our red LED into the base of our NPN transistor, which is also being offset by our regular D3 diode. And the decimal point is connected to our 100 ohm resistor through the collector of our NPN transistor. So that's what's being controlled there. And then everything is, of course, being dropped across our green D2 LED at the bottom. So we power up the circuit. Again, a couple of things happen here. Number one, we obviously see that the 0 is flashing there. And when the 0 goes out, our decimal point briefly lights up. And in conjunction with that, our red LED lights up with the decimal point, and we all get flashing down here at our green LED as well, and we can hear the output of the alarm IC through our speaker every time the 0 appears there. So again, what's happening is that when the alarm IC is triggered, it's sending output through our speaker, which we're hearing, and then it lights up the 0 segment of the display here. When the alarm IC turns off, then the current is going back through our speaker through our red LED here, and we see it briefly turn on because of that. And because of it, our base NP of the NPN transistor allows it to turn on, and that makes our decimal point light up there briefly, and we can see the difference in current between when the transistor is active and when the alarm IC is active. And because of how it alternates there with the output of the alarm IC, that's how we get the different showing of both the 0 and the decimal point. So that's how Project 651 works. And now we're going to look at Project 652, which is the stepper motor with lamp and LEDs. So here we are at Project 652, the stepper motor with lamp and LEDs. There it is in the book, and here it is on the board. So this is actually similar to a bit of a previous project, I think, where we had the alarm IC here instead of the music IC. So we've got a 6-volt supply controlled via our slide switch, which is feeding our music IC. So we both have our green LED here for providing the feed, and then we've got a regular D3 diode, which is connected to the hold function, so it's going to repeat. And then its output is connected to our motor with the fan attached. And then we also have power control for our music IC going through the relay here. And the relay is doing two things. One is that the music IC will normally run through the lamp here. Now I put the 6-volt lamp here instead of the 2.5, 3-volt lamp that it normally calls for. Again, like in the previous project with the alarm IC, I prefer the 6-volt lamp here because we have a 6-volt supply, so that reduces the chance of you accidentally burning out and damaging your 2.5, 3-volt lamp holder. Otherwise you'll have to replace it like I've done before. So the relay basically connects and disconnects the music IC directly to ground, bypassing the lamp here, and then that's all controlled by the oscillating circuit over here. So we got our variable resistor again. We have our NPN and PNP transistors kind of hooked up in a Darlington transistor setup because the NPN collector is connected to the base of our PNP there, being limited by some resistors. And then we have our capacitors, which are kind of help controlling the amount of oscillation, along with our variable resistor control being able to adjust how much these capacitors charge and discharge. So we turn on the circuit with it in the middle there. Our motor starts up there, and we can see some flashing on our green LED there. We can hear our relay and visually see it clicking away. We can also see flickering on our 6-volt lamp here. And with the motor, we can hear the music IC's output being played back through the motor there because, you know, it's got magnetic winding, so it's behaving like a speaker. And we can, of course, control the level of oscillation by adjusting our variable resistor just like in other projects. And they call it a stepper motor because every time the relay is being energized and de-energized, connecting and disconnecting ground directly, we're affecting the output of the music IC, controlling the basically burst of current to the motor there, where it can speed up and slow down, so it runs in steps, making it a stepper motor. So that's how Project 652 works, and now we're going to look at Project 653, which is the IC start and stop. So here we are with IC start and stop, project number 653. There it is in the book, and here it is on the board. So the circuit is relatively simple. I think we had a setup like this before. We got 6-volt supply going to our 7-segment LED. It's been set up so that it displays the number 5 or letter S, depending which way you interpret it. We have our alarm IC, which its output is driving the base of our PNP transistor, and that is got both our motor and our lamp, 6-volt lamp across it, while of course also supplying the feed for our 7-segment LED. And the alarm IC is then being controlled by the output of the music IC, and then we got everything dropping it here with our regular D3 diode. So when we power up the circuit, our 7-segment LED lights up there showing the letter S. You can hear the motor and see it spinning. You can also see that our light is lit up. And then if you watch, everything will turn off here momentarily and start back again, just like that. And you can probably hear some noises being emitted from the motor there, because again it works like a speaker coming out of our alarm IC. And it sounds a little funny because the music IC is driving the alarm IC, which then its output is then driving our PNP transistor there, which again is controlling the out for the motor and lamp here, along with the 7-segment LED. So the music IC is on repeat. So the music IC plays this little music thing, which is driving the alarm IC and everything else, and then when it completes, it stops and then restarts, which is why we get that momentary drop when everything turns off and then starts again. Hence why they call it IC start and stop, because the music IC is controlling the start and stop of everything else in the circuit here. So that's how Project 653 works. So we're now going to move on to Project 654, which is IC motor speed. So here we are at Project 654, the IC motor speed. There it is in the book, and here it is on the board. So it's pretty similar to the past project. We kind of just reoriented some things with our red LED and 6-volt lamp there, and also changed some connections around on our 7-segment LED here, along with putting our green LED there. So when we turn on the circuit this time, our motor speeds up quite a bit and our red LED is nice and dim, and you see that it momentarily pulsed there when the music IC stopped and then it was restarted again. Still have showing the letter S or number 5 depending on your interpretation, and our green LED is lit up nice and bright there, which is helping to feed it, along with our 6-volt lamp, which is in series with our motor there. And we can adjust the speed of the motor a little bit by putting on an additional connection to our alarm IC there. So that affects the alarm IC's output, which of course drives the circuit a little bit differently. And the easiest way is to pay attention to our 6-volt lamp there, because it changes ever so briefly with the different input that we're providing to the alarm IC there. So that's how Project 654 works, and now we're going to look at Project 655, which is the sound and light flasher. So here we are at Project 655, the sound and light flasher. There it is in the book, and here it is on the board. So we got our 7-segment LED. It's been set up to pretty much display a 6 character. We still have our PNP transistor that has our motor that also drives the 7-segment LED and our 6-volt lamp. And then we have kind of a thing set up here with our alarm IC with our NPN transistor, which I just which of course is, being turned on and off, controlling certain inputs to our alarm IC there, which you hear the output from. It goes to our red LED. Got a resistor and regular diode coming off our PNP, and because I didn't have an additional 3-snap, I'm just using the 2.5 3-volt lamp here as a 3-snap because it's low enough resistance it's not really going to impact the operation of that. So we turn on the circuit. We can hear the output of the alarm IC because it's being turned on and off rapidly via our NPN transistor there. And then our PNP is getting the output from that, which is being fed to our motor, 6-volt lamp, and 7-segment LED. And of course we also have some of the output being heard from our speaker and our red LED there, which is flickering with that output as well. So that's how Project 655 works, and that concludes this set of Snap Circuits projects.